Okay, so now let's see what's coming next. So we are here, that property. So we have defined what was an eigenvalue and the corresponding eigenvector. You know that one doesn't come alone; they have to come together, and the eigenspace. So with the first property here. So we said that that's going to come very naturally. Uh, A has an eigenvalue, eigenvector couple V. That's what it means. So we said that the eigenvector also corresponds to the null space of A minus lambda identity, because it means that A minus lambda times identity V is equal to 0. So let's sum up the facts, and so that implies that, well, the null space as V must be different from 0, otherwise it's has no meaning. It's not an eigenvector, so that's in the definition. First requirement is that it's non-zero. It means that the null space of A minus lambda I is not reduced to the 0 element. Okay, that's the first item we have here in that property. Okay, so what does it imply? If you remember the fact that we are in Rn, okay, we have square matrix, so from Rn to Rn, right? If it is the 0 element, okay, using the rank nullity theorem, if we only have the 0 element, it means that the nullity is equal to 0, so the rank is equal to n, so we have full rank, and then you get that it's invertible, right? Okay, so if we have the contrary, right, if we don't we have more than just the 0 element, so we have the dimension of that null space is more than 0. It's strictly more than 0. Well, it means that A minus lambda I is not invertible, okay? Because then it means that the rank is strictly smaller than n, right? You remember that's just really a consequence of the rank nullity theorem, right? So how do you translate the fact that a matrix is not invertible? Well, you just compute the determinant, A minus lambda I, and not invertible, you said that the determinant must be equal to 0. Okay, so in the end we get that lambda belongs to the spectrum of A. That's the second point in that proposition. Lambda belongs to the spectrum of A, then it is a root of the determinant of A minus lambda I. Okay, and this determinant, well, the equation that you obtain when you compute that is called the characteristic equation of your matrix. Okay, it's something you already maybe have heard of, or maybe a term that you've used in a different context. But well, this is the characteristic equation of a matrix. That's the equation you get when you compute determinant of A minus lambda I. It's going to be an equation with the variable lambda. Okay, and it's going to be an order n polynomial. All right, basically just because let's picture you've got your matrix of size 3. If you write that's your matrix A, minus lambda I means that you're just going to write minus lambda on the diagonal, and then you just have to compute the determinant of this, and it's going to begin, if you expand, for instance, according to the first column, that's going to be that times the determinant of this, which is this term times this term minus this one. Okay, and plus some more terms. But the thing is that that first part of the determinant is already going to be an order 3 polynomial. Okay, and you can extrapolate this characteristic equation that you obtain is just going to be an order n polynomial. Okay, maybe we can take an example, simple one, right? 3 1 0 2, that's your matrix A, small matrix, order 2 matrix. All right, let's compute the eigenvalues. All right, so looking for the eigenvalues, I just write the characteristic equation, which is, so maybe I should write it as, so it's a key, the Greek letter key of lambda is equal to the determinant of A minus lambda times the identity. So that's the determinant of 3 minus lambda, 1, 0, 2 minus lambda. Okay, I only have minus lambda on the diagonal, and that's just 3 minus lambda times 2 minus lambda minus 1 times 0, so that's all we have. And it's already factored. Actually, when we have a triangular matrix, it's always going to be already factored, and you get that 3 and 2 are the eigenvalues. Okay, maybe one more example. If you've got, let's say, this matrix again, a 2-2 matrix, maybe you can do that. Pause the video now and find the roots of this equation. Okay, so have you found that? So we just write b minus lambda I, and I compute the determinant, and that's 1 minus lambda for 1 minus lambda. Determinant of this, that's 1 minus lambda, sorry, square minus 4 lambda 2 minus 2 lambda plus 1 minus 4 minus 3, so the delta b2, so that's 4 minus 4 times minus 3, so that's plus 12, so that's 16. So my two roots are just going to be 2 plus or minus square root of 16, that's 2 divided by 2. In other words, that's going to be 3 and negative 1 are the possible roots of this determinant, okay, of this characteristic equation. So these are the eigenvalues. All right, so you can find actually the eigenvalues independently of the eigenvectors, but then you need to find the eigenvectors. Let's see what comes next in our document, and we okay, and we will find the eigenvectors, sorry, associated to these eigenvalues. Okay, so next we have that the multiplicity mu lambda of an eigenvalue is the order of the root of the characteristic equation. Okay, so we saw that roots, eigenvalues were roots of the characteristic equation. Characteristic equation is a polynomial of order n. So what do you know about polynomials of order n? They're all, you have exactly n roots, maybe not distinct, maybe multiple roots in C. And you will have at most n roots in R, okay? So exactly n in C and at most n in R. So usually we tend to, we want to diagonalize in R, so we're going to look for the roots that belong to R, right? So we will have at most n roots in R. And well, the multiplicity of that eigenvalue is going to be the order of the roots in the characteristic equation, right? For instance, let me show you one that you can try later. So let me give you this matrix. So that would be 3, 0, negative 1, 2, 4, 2, negative 1, 0, 3. Maybe you have some time now, but try to find the eigenvalues. You will see that if you compute the determinant, you will obtain that the characteristic equation can be rewritten as 4 minus lambda to the square times lambda minus 2, and probably I've got yeah, well, that's probably a minus here. Okay, so we can factor this. You can show, well, you can do the calculation later on, that these are the roots. So I would have that the eigenvalues lambda 1 would be 2, lambda 2 would be 4, multiplicity usually denoted with a mu of lambda 1 is 1 because it's just a single root, and multiplicity of lambda 2 is 2 because it's a double root. Why? Because it's comes with a square in the factorization. Okay, so that's just definition, a multiplicity of a polynomial. Okay, and you've got some nice properties that can be useful in dimension 2. For instance, the product of eigenvalues is equal to the determinant of the matrix. The sum of the eigenvalues is equal to the trace of the matrix. And before we go on, let's just find in the first two examples that we have, let's find the eigenvectors. Okay, so let's find the eigenvector for that matrix A. So I'm looking at this matrix A. 3, 1, 0, 2, and we said eigenvalues are 3 and 2. Okay, so let's find first the eigenvector associated to eigenvalue 3. Okay, so what do? We know that it belongs to the null space of A minus 3 times I. So we're looking for the null space of A minus 3 times I. Minus 3 times I. Okay, so what do? I write my matrix A minus 3I, so that's just going to be 3 minus 3, that's 0, 1, 0, 2 minus 3, that's -1. Okay, and I want to find all the elements of R2 that are going to make this equal to 0, right? So what do we have? We just have that y should be equal to 0 and nothing on, no condition on x. So what does it mean? It means that anything that is going to be collinear to 1, 0 is going to satisfy this equation. Of course, we have an infinity of solutions, because don't forget that the null space is actually a vector space, right? So we know that we will have an infinity of solutions. We want to find the spanning family of this solution, right? And the thing is that here we've got one spanning vector. It's going to be anything that is collinear to 1, 0. So, oh, sorry about this. I can write that the eigenvector the eigenspace associated to eigenvalue 3 is going to be the span of this vector. Okay, and what about the eigenvalue? We said the other one was 2. I have to find the null space of A minus 2 times I. Null space of A minus 2 times I is just 3 minus 2, that's 3 minus 2, that's 1. Then I've got 1, 0, and 2 minus 2, this is 0. So I'm looking for xy such that this is equal to 0. Oh, sorry, that's 1, not 2. 3 minus 2. Okay, so what equation do I get? Or you can say what is free variable y, and linked variable is going to be x. So if y is equal to 1, x should be equal to -1. Okay, so you can choose that one or the opposite one. They're just going to be collinear, and we can say that the eigenspace associated to eigenvalue 2 is the span of this eigenvector. Okay, so that's eigenvector, and the eigenspace is the span of this eigenvector. Okay, so you know how to find eigenvalues, you know how to look for the corresponding eigenvectors. Next question is, what can we do with these, and how can we diagonalize our matrix?